Jai Hind students, welcome to my YouTube channel. And students, before we start today's session, I must share a thought with you. Students always believe in hard work and don't hesitate to fly high. Actually, I will suggest you to add wings to your imagination and never ever hesitate to fly high. Dream big, and in order to realize your dreams, make concentrated and dedicated effort. So with that, let's begin today's session. As I promised in the previous session that we'll be discussing some more numericals based on Biot Savart law and its application. So here it is. I've come with another set of 9 questions. In each of these 9 questions, we are supposed to find out the strength of the magnetic field at point O due to these different current carrying systems, right? So let's proceed with question number 1. As we have discussed, we need to divide it into parts. Suppose the straight portion, this is part 1. This circular portion, actually this is in the form of an arc. This is suppose the second portion, and this again the straight conductor. This is the third portion. Now students, we are aware the magnetic field at a point on the axis of a straight conductor is always 0. Therefore, the magnetic field at point O due to this straight conductor and this straight conductor, as point O lies on its axis, it will be equal to 0. So B1 equals to B3, each is equal to 0. So we are left with only this second portion. So let's find out the magnetic field due to this portion, B2. Now this is an arc. It is subtending this angle at the center. That is 360 minus 90. That would be 270 degree. So this is theta. It needs to be converted into radians. So what is the formula to find out the strength of the magnetic field at the center of an arc subtending angle theta at the center? The formula is mu naught I theta divided by 4 pi r. R is the radius of the arc under consideration, right? So the only thing which we are left to do is we need to convert this theta 270 into radians, right? So we are aware of the conversion, isn't it? So we are aware 360 degree, it is equal to 2 pi radian. So 1 degree will be equal to 2 pi by 360 radians. Therefore, 270 degree, it will be equal to 2 pi by 360 into 270 radian. So let's solve it. So 9 3, 9 4 36. So it will be equal to 2. So it is 3 pi by 2 radian. So 270 degrees in radians would be 3 pi by 2. Clear students? So let's substitute this value over here. So what we get is B2 is equal to mu naught I divided by 4 pi r. In place of theta, write 3 pi by 2. So pi get cancelled. So we get 3 by 8 mu naught I divided by r. So this is the strength of the magnetic field at point O. 3 by 8 mu naught I divided by r. This is the magnitude. Now magnetic field being a vector quantity, obviously it possesses both magnitude as well as direction. So what about the direction? Current is flowing in the anti-clockwise, isn't it? So it will be in the outward direction. Look, apply this rule. So it will be perpendicular to the plane and directed outwards. So it is written like this. This symbol represents the direction of the magnetic field which is perpendicular to the plane and directed outwards. Right? So we are over with question number 1. And students, remember, if in a circular loop the current appears to be flowing in the clockwise direction, then at the center the magnetic field will be directed inwards. And in case in a loop the current appears to be flowing in the anti-clockwise direction, then at the center the magnetic field lines will seem to be coming outwards. Just remember these 2 points, right? Okay, we are going over with question number 1. Let's proceed with question number 2. These are the two straight current carrying conductors, and our objective is to determine the magnetic field at point O. And this is the origin, right? And the coordinates are AA. So it is equidistant. So this distance is A and this distance is also A. So obviously it's the case of this is a square, isn't it? So if you join this, then obviously this is 90 degree, this will act as a bisector. So this angle would be 45 degree, this angle would be 45 degree, right? So let's consider this to be part 1, this to be the second part. So let's first calculate B1. Magnetic field at point O due to this section. It's a straight conductor. One end is extending to infinity, the other one is having a fixed point. And this end is making an angle of 45 degree with this reference line. So what's the formula? It is mu naught I divided by 4 pi perpendicular distance, that is A, sin 90 plus sin 45 degree. It is sin 90, which will be 1, plus sin 45 degree. And what will be the direction? Just make use of right hand thumb rule. So direction of magnetic field at point O would be inwards. So this is in the inward direction. Sin 90 is 1, sin 45 degree is 1 by root 2. So what do we get is mu naught I divided by 4 pi A 1 plus 1 by root 2, directed inwards. Now let's find out the strength of the magnetic field at point O due to this second conductor, right? We'll get the same expression obviously. It will be mu naught I divided by 4 pi A 1 plus 1 by root 2. Again, it is directed inwards at point O. Due to the second current carrying conductor, the magnetic field lines will be directed inwards, right? So here at point O, the magnetic field due to the first and the second section both are of equal magnitude as well as in the same direction. So they will get added up. So net magnetic field, it will be equal to B1 plus B2. So substitute this value B1 and B2, both are equal, it will become twice. So we get twice mu naught I divided by 4 pi A 1 plus 1 by root. So that in turn will give us mu naught I divided by 2 pi A 1 plus 1 by root and directed inwards. Clear, students? So we are over with question number 2 as well, right? Let's proceed further. Let's proceed to question number 3. Question number 3 is also pretty simple. We need to directly apply the formula. It is in the U shape. Again, at point O, we are supposed to calculate the net magnetic field. It can be divided into 3 parts. This is a straight part, 1. This is a semicircular part of radius r. This is second. And this is again a straight infinite long conductor. This can be considered to be third, right? So let's calculate the magnetic field at point O due to the first section, right? This is the first section. Its perpendicular distance is r. One of the end of the straight conductor is making an angle 0 with the reference line and the other one is making an angle of 90 degree, right? So what is the formula? Mu naught I divided by 4 pi perpendicular distance r. Sin phi 1 plus sin phi 2. One of the angle is 90 degree, the other angle with the reference line is 0 degree. Sin 90 is 1, sin 0 is 0. So 1 plus 0 is 1, so we'll be left with only mu naught I divided by 4 pi r. And students, what will be the direction at point 2 due to this first conductor? It will be like this. So at point O, the field lines will appear to come out. So it will be perpendicular and directed outwards. So that is represented by this particular symbol, right? Now let's find out B2 due to the semicircular section. What is the strength of the magnetic field at the center of a semicircular current carrying loop? It is given by mu naught I divided by 4r. Now what about the direction? Current is flowing in the anti-clockwise direction. So magnetic field at the center will be directed outwards. isn't it? Like this. It's directed in the outward direction. Now B3. Due to this straight conductor, the magnetic field at point O, again, it will have the same magnitude as that of the first conductor. So what you get is, it will be mu naught I divided by 4 pi r. What about the direction? Again, make use of right hand thumb rule. So that will give us the direction of the magnetic field at point O to be in the outward direction. So students, it's pretty clear. The magnetic field due to each of these three current carrying portions at point O is directed outwards. So the net magnetic field at point O would be given by the addition of these three, and it will be directed outwards. So the net magnetic field is B1 plus B2 plus B3 and directed outwards, right? Let's substitute the value. We can take mu naught I divided by 4r as common. So this is 1 by pi plus 1 plus 1 by pi. That will give us mu naught I divided by 4r 2 by pi plus 1 and in the outward direction. So students, this is the magnitude and this is regarding the direction, right? So we are done with question number 3 as well. Now let's proceed further. Question number 4. That is an interesting question. Actually, 2 loops are given. In question number 4, 2 identical, circular and concentric loops are given, whose planes are perpendicular to each other. Just check that diagram. We are supposed to find out the expression for the magnetic field at the common center. So again I repeat, question number 4. It's the case of 2 identical current carrying loops, each of radius r, each carrying current I, and both are concentric, that is having common center, but their planes are perpendicular to each other, right? We are supposed to find out the net magnetic field at the common center. So let's try this particular question. So how to proceed is, here, suppose this is loop 1, this is loop 2, right? Let's consider first loop. In this case, it's appeared to be flowing in the clockwise direction. So here the magnetic field line will enter, and from the other face the magnetic field line will come out, isn't it? So this is suppose point 2. So the magnetic field would be perpendicular to the plane of loop 1 and will be directed towards right. So this is suppose B1. What about the direction for the magnetic field at point 2 due to the second loop? Current is flowing in the anti-clockwise direction. So here the magnetic field lines will be perpendicular to the loop and in the outward direction. So it will be like this. This is B2. What about the angle? It is 90 degree, isn't it? Also, B1 is equal to B2 is equal to B, say. Both are identical, both are of the same dimension, same current is flowing through each of these 2 circular loops. So at the center, the magnetic field due to a circular loop is given by mu naught I divided by 2r, isn't it? Now look, magnetic field always, remember students, it's a vector quantity. So while solving numericals dealing with vector quantities, we have to make use of laws of vector addition. Now these 2 vectors are inclined at an angle of 90 degree. So the resultant magnetic field would be given by square root of a square plus b square, that is b1 square plus b2 square. Both are of same magnitude. So it will be equal to root 2b. So root 2 and the value of b is mu naught I divided by 2r. So this is the magnitude of the magnetic field at the common center. Now what about the direction? Students, if the 2 vectors are equal in magnitude, then the resultant always bisects the angle between them. So this is the resultant. This is the resultant magnetic field. So it will be making an angle of 45 degree with either of B1 and B2. Right? So this is the magnitude and this represents the direction. Clear, students? Okay. Let's proceed to question number 5 now. It's a question which we will try to answer in terms of unit vectors I cap, j cap and k cap. Now as you are aware, this is x axis, this is y axis, this is z axis, right? So x axis, it is represented by I cap, y axis, it is represented by j cap, and z axis, it is represented by k cap, right? And these are the three sections. This is first one, this is semiconductor second, semi-circular loop, this is second, and this is again a straight part which is third. This semicircular portion, it lies in the xz plane, the horizontal one, right, in this particular case. So let's try to analyze. And we are supposed to find out the net expression for the magnetic field at point O. So what to do is, let's find out the expression for the magnetic field due to this first portion. At this point, the direction of the magnetic field would be like this. From point 2, the field lines due to this first portion will appear to come out. So this is z axis, isn't it? This is x axis, this is y axis, and this one is z axis. Direction will be given by k cap, right? So due to this conductor, first one, the magnetic field lines will be directed along z axis, that is towards k cap. So its direction will be towards positive z axis. Now what about its magnitude? The magnitude is given by mu naught I divided by 4 pi perpendicular distance, that is r. So this is the magnitude and this is the direction of d1, right? Now consider second one, semicircular current carrying loop. What's the formula for the magnetic field at the center of the semicircular current carrying loop? It's mu naught I divided by 4r. Now what will be its direction? It is in the horizontal plane, xz plane, and current is flowing in the anti-clockwise direction, isn't it? It's flowing in the anti-clockwise direction. So the magnetic field at the center would be perpendicular to the plane and directed outwards. So at this point, the magnetic field will be directed along y-axis. So that is j cap. Clear, students? The current in the circular loop is in the anti-clockwise. So as a result, the direction of the magnetic field at the center would be perpendicular to the plane of the semicircular loop and will be in the outward direction, that is in the upward direction, which is indicated by y-axis. In turn, it is represented by j cap. Now what about B3? B3 is again in the straight portion, isn't it? So the magnitude will be same as that of B1. And what about the direction now? Look over here. So from point 2 again, the field lines due to this third section will appear to come out. That is along this z axis. That is, it will be k cap. So therefore, net magnetic field would be given by B1 plus B2 plus B3. So it will become twice. So what you get is mu naught I divided by 4 pi r. This is k cap plus j cap plus k cap. So it is mu naught I divided by 4 pi r 2k cap plus j cap. This is the representation of the magnetic field at point 2 in terms of I cap, j cap and k cap. Right? So this is how these questions are to be done. In the similar manner, we can try sixth question as well. In the sixth question also, we are supposed to determine the magnetic field at point O, and we are supposed to represent the result again in terms of I cap, j cap and k cap. Right? Let's proceed. Question number 6. Okay. This is a straight portion parallel to x-axis. This is a semicircular portion, right, lying in this yz plane, and then again this portion, it is going along z-axis. This is the z-axis, this is the z-axis. So this is it. This is a straight conductor parallel to x-axis, then a semicircular portion lying in the yz plane, and then the wire is extending to infinity along the z-axis. We are supposed to find out the magnetic field at the point O. So let us consider this to be the first portion, the semicircular section to be the second one, and this one along the z-axis, this is third one. So let's find B1. B1 is the magnetic field due to the straight portion at point O, right? So what's the formula? What's the magnitude? It's mu naught I divided by 4 pi r. R is the proper distance of this observation point from the straight conductor. Now students, what about the direction? This is x-axis, I cap, this is y-axis, j cap, and this is z-axis, which is represented by this. It will give us k cap, right? So here, the direction of magnetic field at point O due to this first portion, it will be like this. From point O, the field lines will appear to come out. So at point O, the magnetic field will be directed along z-axis. And the direction of z-axis is represented by unit vector k cap, right? So it will be represented by mu naught I divided by 4 pi r k cap. This represents magnitude and this one will represent direction. Now due to this semicircular portion, the magnetic field at the center, its magnitude is given by mu naught I divided by 4r. Now regarding its direction, look students, you need to analyze this portion very carefully. The situation is like this. There is a straight part which is parallel to the x-axis, and there is a semicircular portion lying in the yz plane, and then the last part, third section, it is along z-axis, extending to infinity. So in this case, the current is flowing in the clockwise when seen from here. So it means that the direction of the magnetic field at point O would be directed inwards, or it will be along x-axis. So it will be I cap. Now the third part is left. This is the third part. The current is flowing along the positive z-axis. So apply this rule. The thumb, it is pointing along the direction of the flow of current. So the direction in which the rest of the fingers curl, it is like this. So at point 2, by drawing a tangent, you will get the direction of the magnetic field towards the negative x-axis. So it will be minus I cap. Positive x-axis, that is represented by plus I cap. Negative x-axis, that direction is represented by minus I cap. And magnitude due to this straight conductor at point 2 would be same as that of B1. That is, we will get mu naught I divided by 4 pi r. Right? So net magnetic field, it will be equal to B1 plus B2 plus B3. So that will give us mu naught I divided by 4r. This can be taken as common. So here we will be left with k cap by pi. Here we will be left with plus I cap, and here we are left with minus I cap by pi. So this is the complete solution, right? So these are the portions where the strength of the magnetic field has to be expressed in terms of I cap, j cap and k cap. I cap, j cap, k cap are the unit vectors representing the direction along x-axis, y-axis and z-axis respectively, right? Okay, we are done with question number 6 as well. Now let's proceed to question number 7. Students, question number 7 is very important one. Mark an asterisk symbol for this particular question. This is very important from competitive point of view as well, right? So this is pretty important. Okay, this is the situation. This is a straight conductor. The point O is lying on the axis of this conductor. This is 1, this is 2, this is 3 and this is 4. These two parts, the straight ones, point O lies on the axis of these straight parts, right? So B1 is equal to B3 is equal to 0. Point O lies on the axis of this straight portion, right? So as a result, the magnetic field at a point on the axis of a straight conductor is always 0. So B1 equals to B3, both is equal to 0. Now consider B2. Suppose its length is L1 and suppose the length of this minor arc is L2, and also consider I be the net current entering. This point will act as a junction. So suppose current I1 flows through it, and suppose over here current I2 flows through it, and they both will combine at this junction, and the net current would be I, which is equal to I1 plus I2 using junction rule, right? So through this major arc of length L1, current I1 is flowing. Through this minor arc, current I2 is flowing, right? Lengths are considered to be L1 and L2 for the major arc and the minor arc respectively. I is the net current entering and leaving this junction. So as per the junction rule, net current I is equal to I1 plus I2, right? So B2, magnetic field at point O due to this current carrying arc. Formula is mu naught I1 is the current, divided by 4 pi radius R and the angle which it subtends. Suppose it subtends angle theta 1. This one will be angle theta 1, this entire angle. It will be theta 1 and we present it to be theta 2. Clear, students? What will be the direction? It is in the clockwise direction, so it will be inwards. If in a loop the current appears to be flowing in the clockwise direction, then at the center the magnetic field is directed inwards. Now theta 1 can be represented in terms of L1 and R1. Angle, as you are aware, it is length of the arc divided by radius. So theta 1 may be written as L1 by R. So what do we get this? B2 is equal to mu naught I1 divided by 4 pi. Substitute this value of theta 1. So here we will get R square and directed inwards. Similarly, students, the magnetic field due to this fourth portion, right? What would be the magnitude due to this fourth portion of length L2? Just use the same logic. What do we get? Mu naught. What is the current flowing through this section? I2. Length of this section is L2 divided by 4 pi R square. Radius is same. But in this case, the current is flowing in the anti-clockwise direction. So the magnetic field at the center would be directed outwards. So this is it. So we have obtained B1, B2, B3 and B4. B1, B3 will not contribute anything towards the net magnetic field, each being equal to 0. Consider on B2 and B4. Both are given by these expressions. One is directed inward, the other one is directed outwards. Now the most important part. Students, these two are connected in parallel. Suppose this length offers resistance R1 and this offers R2, right? So it is equivalent to this particular circuit. This is the net current entering, this is the junction. Suppose this is point A and this is the point B where the current leaves. Here I1 is flowing and here I2 is flowing. This part offers resistance R1, this part offers resistance R2. So these two parts actually they are connected in parallel because both the ends of these two are connected between the same two common points A and B. So the potential difference across these two parts are same or constant. That is why they are said to be connected in parallel. So students, since they are connected in parallel, therefore potential difference across the first one, it should be equal to the potential difference across the second current carrying portion. And as per Ohm's law V1, we are aware it is I1R1 and it is I2R2. Resistance, it's rho L by A. So it is I1 rho L1 by 3. I2, it is rho L2 by A. Rho is the resistivity which for a given material is constant. A is the cross-section area. Here obviously we have considered the entire portion to be of uniform cross-section area. So A is constant. So what do you get? I1 L1 is equal to I2 L2. Put this as equation number 3. This as equation 1, this as equation 2 and this as equation number 3. So students, observe these first, second and third equation. I1 L1 is equal to I2 L2. So therefore, magnitude of B2 is equal to magnitude of B4. From 1, 2 and 3, we conclude that magnitude of B2 is equal to magnitude of B4 actually. So both are of equal magnitude, but one is directed inwards, the other one is directed outwards. So both being equal in magnitude and oppositely directed, they tend to nullify the effect of each other. So the net magnetic field at the center is 0. Net magnetic field at the center, it would be equal to 0. Clear, students? And this concept is valid not only for circular loop, it's valid for any loop of any shape, be it a square shape or be the loop in a triangular shape, like this. This is suppose a square loop, and current is entering on one side and the current is leaving the other corner. So the net magnetic field at the center, due to this square current carrying loop, here it would be 0 using the same concept. For a triangular loop also, if the current enters one corner and it leaves the other corner, the net magnetic field at the center due to this triangular current carrying loop would be 0. So apply the same logic and you can easily derive it mathematically. This is I1, this is I1, this is I1, and this will be I2. So this is an assignment for you. Prove that the magnetic field at the center due to this square or due to this triangular current carrying loop is 0. Right? So by using the same logic, you can easily justify the answer. So students, let's proceed to question number 8. Question number 8 is relatively simple. The system consists of two straight conductors. They are not intersecting. And these are the two independent current carrying conductors, each carrying current I. So let's consider this to be the first one and this to be the second one. So let's calculate the magnetic field for the first conductor. This one is the first conductor, right? And its proper distance from the observation point is A. Its both ends extends to infinity. So what's the formula? It is mu naught I divided by 2 pi r. What will be the direction? Like this, current is flowing along this direction, so the magnetic field lines will be in the outward direction. Outward, that's represented by this. Consider V2. This is again a straight conductor, both ends extending to infinity, and the distance of this observation point, upper distance, is A. So we have got the same magnitude. And what about the direction? Like this. It's in the inward direction. So as a result, we can easily say both B1 and B2 are of equal magnitude, but they are oppositely directed. So again, they will tend to nullify or cancel out the effect of each other. So the net magnetic field at point O would be 0. Because these two are of equal magnitude but oppositely directed. One directed inwards, the other one directed outwards. So they will tend to cancel out the effect of each other, right? So the net magnetic field at point O due to these two straight infinitely long conductors is 0. Okay, let's proceed to the last one, ninth question. It's a loop which is in the form of an arc. So consider this straight portion to be 1, this portion, curved portion to be 2, and this one to be 3rd. Now look, point O lies on the axis of straight portion 1 and the straight portion 3. So B1 is equal to B3 is equal to 0. Always remember, students, the magnetic field at a point on the axis of a current carrying conductor, straight conductor, is always 0. So these two portions, current carrying portions, will not contribute towards any magnetic field at point O. Let's consider B2. Due to this arc, it is subtending an angle of 300 degree. Right? We need to convert it in radians. So anyway, what's the formula for a current carrying arc? The magnetic field at its center. The formula is mu naught I divided by 4 pi r multiplied by theta. Here I must mention that theta needs to be represented in terms of radians. So let's convert 300 degree into radians. So as I told you, 360 degree is equal to 2 pi radian. So 1 degree it will be equal to 2 pi by 360 radian. Therefore, 300 degrees it will be equal to 2 pi divided by 360 into 300 radian. So it will give us pi by 3 into 5 radian. that is 5 pi by 3 radian. Clear, students? So we get B2 is equal to mu naught I divided by 4 pi r, theta in place of theta, write 5 pi by 3. So what we get is 5 mu naught I divided by pi get cancelled, 12 r. So this is the net magnetic field at point O. And regarding the direction, students, current is flowing in the clockwise direction. So magnetic field at the center would be directed inwards. So this will be the direction. So we are over with another set of 9 questions. I hope you have understood each and every question. Do practice these questions and try to do some additional questions as well, right? So that's it for this particular session. We'll continue in the next lecture. Do join me then. Till then, do take very good care of yourself and bye-bye.